Okay, let's get right into it. This project is all about the development and performance evaluation of a multi-band LTE/5G antenna, specifically designed for intelligent vehicular communication.
So here's how we'll break it down. We'll start with the project overview, then dive into the antenna design concept. After that, we'll cover optimization and fabrication, and I'll justify the array configuration we chose. Finally, we'll look at the measurement and field testing, which leads us to the key results and the main engineering takeaway.
All right, let's start with Section 1, the project overview, and the problem we're trying to solve here.
So, what's the core issue?
Well, trying to maintain reliable LTE or 5G connectivity in a moving vehicle, it's a real challenge. You've got all these environmental factors at play, and on top of that, most commercial antennas just aren't optimized for this, leading to dropped signals and unstable connections.
So, our main engineering objective was clear. We needed to design, analyze, and most importantly, validate a compact multiband antenna that's truly optimized for these demanding conditions.
Okay, moving on to the design concept. We took what we call a simplified, robust approach here.
For our base element, we went with a microstrip patch antenna. Why? Well, it came down to two really practical reasons. First, it has a very low profile, which is obviously crucial for vehicles. And second, it's just straightforward to integrate into the vehicle's platform. Now, getting dual-band operation at 2.6 and 3.5 GHz was a key goal, and we managed to do it without making the design more complex. How? We're leveraging the patch's natural physics, using its fundamental resonance for the LTE band and a higher-order resonance for the 5G band.
And this was a very deliberate choice. We could have used complex slots or parasitic elements, but we actively avoided them. The goal was to keep the design simple, which makes it more robust and, this is a big one, much easier to manufacture consistently and reliably.
So, this is what the final 2x1 array looks like in our CST simulation. As you can see, the geometry is very clean, and that's a direct result of that simplified design philosophy we were just talking about. Okay, so we have the model. The next step, of course, is turning that simulation into a physical prototype. The simulations looked really promising. We got excellent impedance matching, with the S11 response well below the -10 dB mark, right where we needed it, at both the 2.6 and 3.5 GHz bands.
And here's the first physical result. This is our optimized single-element design, fabricated on a standard, cost-effective FR4 substrate.
But, things are never that simple. We hit a real-world engineering snag. The fabrication tolerances on the FR4 actually caused a small frequency shift on our first go. So we had to go back, make some calculated adjustments to the parameters, and fabricate a second prototype. That second one worked exactly as planned. Right, so why did we move to an array? This next section is all about justifying that decision, which really comes down to needing higher gain.
The single element worked, don't get me wrong, but its simulated gain was about 3.5 dBi. And frankly, that's just not enough for a really solid, robust connection in a moving vehicle. That limitation is exactly what pushed us towards building an array.
This brought us to a classic engineering trade-off. We did simulate a 4x1 array, and sure, the gain was higher, but it was just too big, and its feed network was so complex that it would have been a nightmare to fabricate reliably on FR4. The 2x1 array, on the other hand, gave us a very healthy 78% boost in gain, but it was still a manageable size with a simple feed network. It really hit that sweet spot between performance and practicality.
So, with our 2x1 array designed and fabricated, it was time for some real-world validation. Our testing methodology was pretty thorough. We started in the lab, of course, measuring S parameters with the VNA. Then we took it out on the road for a vehicular drive test using a MikroTik LTE kit. We recorded the RSSI along a main road and a semi-rural route, and we benchmarked our antenna's performance against the kit's built-in antenna and a typical commercial one. So during the drive tests, our fabricated prototype went head-to-head with a standard internal LTE antenna. All right, let's get to the payoff. This last section is where we look at the quantified results and the final engineering takeaway from all this work.
And the results really speak for themselves, especially on the semi-rural route. You can see a clear, direct link between gain and real-world performance. As we step up in gain, from the internal antenna to our single element and finally to the 2x1 array, the coverage distance consistently gets better. Our final 2x1 array with its 6.18 dBi of gain delivered the best range of all.
So, to sum it all up,
Our fabricated 2x1 array proved to be a genuinely practical and reliable solution for vehicular LTE. It delivered a measurable, data-backed improvement in both signal strength and coverage distance. Ultimately, it successfully achieved the core objective we set out at the very beginning.